talking about the possible planets.
Oh, there's still 3 minutes.
Welcome back, everyone. Oh, now I really can hear myself. Yes. Thank you, Aislinn. Thank you, Osase. Welcome back, everyone, to the afternoon session. We're going to start things off thinking big picture. So we're fortunate to have Phoebe Heretz, who's going to tell us about new technology she's invented to help us understand how the cosmic web of galaxies have changed their metallicity over time. Thank you.
Thank you, Matt, for that introduction. My name is Phoebe Heretz. I am a rising senior at SUNY New studying physics and astronomy. And this summer, I worked with Dr. Dian Triani and Professor Lisa Kewley in search of a new metallicity diagnostic suitable for low spectral resolution surveys of star-forming galaxies. So first, I'll introduce metallicity and why we study it. In astronomy, metallicity is considered the abundance of elements heavier than hydrogen and helium, because it's known that hydrogen and helium were formed shortly after the Big Bang in what we call nucleosynthesis, but all of the heavier elements are only known to have formed in star lives and deaths. So here is a diagram of the periodic table with the element sources. So you see here, we have the Big Bang fusion in blue with hydrogen and helium, and then all of these cool stellar processes that formed the rest of the periodic table. And here's another compelling example. This is the well-known Cassiopeia A supernova remnant. And on the right here, the Chandra team has colored the elements that the explosion created in different colors. So if we understand the metallicity, that's a good indication of chemical evolution across time. It's also, therefore, a good way to understand galaxy evolution. In particular interest these days with the James Webb Space Telescope is understanding galaxy evolution of these very early, very young galaxies. So how do we measure metallicity, this chemical abundance? We use what we call a galactic spectra. So a spectrum is created when you take the incoming light from a galaxy, you put it through a spectrometer, and it breaks it out into all of its component wavelengths. Highlighted here is a very high-resolution spectrum from the Sloan Digital Sky Survey. And what we're looking at are emission lines. So we see hydrogen alpha is very bright here. We see nitrogen 2, sulfur 2, oxygen 3, etc. Now, the most direct way to measure this metallicity is through what we call an auroral line. And this is a temperature-sensitive emission line. The most commonly used one is this O3, 4363 line. And we measure its abundance against hydrogen alpha, which is formed in these star-forming galaxies in the H2 regions that surround the young, hot stars. We also look at oxygen because it's the most abundant of these metals. And here are the units that we use for metallicity. But the caveat is that these auroral lines are weak, and they become difficult to detect, especially at higher metallicities. So researchers had to come up with a new method to measure metallicity. So I'd like to introduce what we call strong line metallicity diagnostics. And essentially, this way of diagnosing metallicity uses those strong emission lines that are available in star-forming spectra, and it uses them in ratios with each other to see if any are good proxies for metallicity. So I'll introduce this figure here. This is a table of studied diagnostics. On the x-axis, we have metallicity from low to high. And on the y-axis, we have the ratio of these emission lines. And these have been studied in the UV panel on top, in the optical range, as well as the infrared range. And here are some commonly used examples used by the community. We have R23, and we also have N2 over O2. And so what we're looking for is hopefully a monotonic trend that has a one-to-one relationship, but we're also looking for one that is tight as well. So I didn't introduce what these colored lines are. This is a galactic property called ionization. And so in blue, we have low ionization. In red, we have high ionization. So what we're looking for is a tight trend, which means it's not too dependent on ionization. So the overall goal of this study is to search for one of these metallicity diagnostics, a new one, that could be suitable for low spectral resolution surveys. So more specifically, we're looking at surveys where H alpha and N2 are blended and O2 is not available, rendering R23, for example, not usable. So we'll look more deeply at what we mean here. So on the left, again, we have the high resolution spectrum from the Sloan Digital Sky Survey. And we see H alpha and N2 are very close to each other, but still resolvable. And O2 is available as well. But with a low spectral resolution spectrum, for example, from the Hubble Space Telescope WFC3 GRISM, we see that H alpha and N2 are now blended in this one line, and O2 is not available. So some example use cases where we'd like to use our metallicity diagnostic are as follows. There's some instruments where this could be applicable, as well as some upcoming all-sky surveys. We think one really compelling use of this diagnostic could be with these all-sky surveys to come up with a statistical baseline of metallicity. So lastly, I'll introduce what star-forming galaxies are. This is what we call a BPT diagram. This is actually a good example of using strong emission lines in ratio with each other to derive galactic properties. And what the BPT diagram tells us is the dominant ionization source in galaxies. So we have the star formation branch, where the dominant ionization are these young, hot stars heating up the hydrogen around them. And then we also have the AGN branch. So the dominant ionization source are the supermassive black holes at the center of these galaxies. We also have distinguishing lines between the branches. The Kaufman line is the empirical line, whereas the Kewley line is the theoretical line that distinguishes them. So next I'll dig into our actual methods, how we conducted our study this summer. So we used the Sloan Digital Sky Survey, DR7, which released about 1 million of these high-resolution spectra of optical spectra. It's the most complete survey that we have of our local universe in the optical range. And we utilized the metallicity calculation that they put forth as our baseline. So honing in on those 1 million galaxies, as I mentioned before, we are interested in the star-forming branch, and we limited ourselves below the Kaufman line. We limited ourselves to quite low redshift, quite local galaxies of a redshift less than 0.2, with a high signal to noise, and that left us with a sample size of about 150,000 galaxies to work with. And the specific emission lines that we were probing to search for metallicity diagnostic are as follows. And again, we selected these emission lines because of the low resolution spectra that we are looking at as our use case. So after probing many combinations of these emission lines in combination with each other against metallicity, here we present our strongest candidate metallicity diagnostic. This is using the H-alpha plus N2 blended line over oxygen 3. And it has what we're looking for. It has, it's monotonic with a relatively steep slope. And these lines are incredibly bright in galactic spectra, so that means that they will be easily detectable. Our results physically make sense as well. N2 and O3 are both known to be dependent upon metallicity, but in opposite directions. So as with higher metallicities, N2 becomes brighter while O3 becomes weaker, and that agrees with our findings. So a big part of our analysis this summer was correcting for dust. This panel that I show here is a molecular cloud at different wavelengths, and this shows us that the dust in galaxies differs depending on the wavelengths that you're looking at. So we are working with several wavelengths in our analysis, so we had to correct for dust for each of them. So dust is an ongoing challenge in extragalactic astronomy because we have to consider the dust in our own Milky Way, but then the dust in the galaxies we're observing. And it can scatter or absorb almost half of the intrinsic light coming from the galaxies. So it's very important. And this is the most robust method that we have so far, is using what we call the Balmer decrement, which is this ratio of hydrogen alpha to hydrogen beta. And in these star-forming galaxies, that intrinsic value should be about 2.86. So we can consider any deviation from that value to be due to dust. And in the interest of time, I'll just present the equations, but next we calculated color excess, and then the intrinsic flux for each of the lines that we used. So here we present our diagnostics dust dependence. And you can see that it does have a dust dependence with the change in slope. But what we're looking for is if the scatter changed much. And that's denoted by the width of the percentile lines. And what we can see is that the scatter does not change significantly, which indicates to us that we could use this diagnostic on dust uncorrected data. So as I mentioned previously, the most robust dust correction method utilizes this Balmer decrement, but it will be unavailable with these low resolution spectra because of the blending of the H-alpha line. So we propose that we could use this diagnostic for uncorrected data, but future work, it is best practice to correct our galaxies for dust. So in addition to surface fitting the dust dependence, we are also going to test other dust correction methods besides the Balmer decrement to see if one is suitable for our diagnostic. So that, what I've shown so far is the empirical study of these potential diagnostics, but we also wanted to approach it from the theoretical side. So to do that, we input galactic parameters into a BPass software, which then output theoretical galactic spectra with varying metallicities as well as ages. We then input those theoretical spectra into the mappings photoionization model. And mappings then outputs these theoretical diagnostics that I introduced earlier. So the results of our theoretical mappings photoionization model is as follows. We see that there is a dependence upon ionization, especially at low ionization levels. So low is denoted by this orange line up here, and it becomes increasingly higher as we travel down. So this is actually a good sign if we want to use this diagnostic for high redshift surveys, because we should assume that at higher redshifts, the universe is younger, star formation is peaking, we should see higher ionization levels, which would agree with this less ionization dependent model below. And we have found with preliminary testing of higher redshift data that this agrees with our model. So that's a good sign of using this diagnostic for high redshifts. Also, we should expect that our SDS galaxies are all within the same parameter space. They're all local, they're all star forming, so they should all have a similar ionization. And our results do agree with that. They all hover at around a ionization parameter of 7. So our future work, I introduced this briefly on the slide beforehand, but we have seen some preliminary results of a redshift dependence, so we hope to calibrate that so that this is useful for high redshift surveys. So we're looking at the MOSDEF data from the Keck Observatory, as well as these two HST surveys. And this very compelling plot I have on the right here is from the NearSpec Cosmic Dawn team. And we have the rest wavelength on the x-axis and redshift from 0 to 12 on the y-axis. And I have highlighted here the oxygen 3 line and the blended H-alpha and N2 lines. And you can see from redshift 0 all the way to 12, where this plot is cut off, these lines are bright the entire time. So it's compelling that we could use this diagnostic across cosmic time, essentially. Very exciting. And years-wise, redshift 12 is past 13.1 billion years in the past. And with that, I want to thank the NSF for funding this research, the Center for Astrophysics for hosting us, my home institution, SUNY New Paltz, for their support over these past 3 years. And everybody listed here, thank you so much. It's been an incredible summer.
Thank you, Phoebe. Thank you, Phoebe, for a great talk. We have time for a couple of questions.
So in one of the later diagrams that you showed, there was like I think there was like a black line sort of fitting on top of that blue data. Can you explain what that black line is?
Sure, that's the median line, so that's the average, essentially.
There's a question in the back.
Yeah, so the plot where you have the Kaufman line and the Kewley line, that plot?
Sure.
I was wondering, if they're supposed to represent sort of like the same thing, it's just different methods, like one is empirical and one is theoretical.
Theoretical, yes.
What is, like, I guess, is there an explanation for like why there is a gap between these two measurements?
Sure. So the question was about the difference between the Kaufman and the Kewley line. So it's essentially that we have these two branches, but we're not sure where exactly they could be mixed in the middle there. So we limited ourselves to below the Kaufman line because we can be more certain that those are all star-forming galaxies and would eliminate any mixing of AGN in that boundary there.
I have a quick question
Sure.
also. I noticed you limited your method sample, if I could call it that, to below redshifts of 0.2.
Mm-hmm.
Do I have that right?
Yes.
And I'm wondering if you would lose lines or brightness or something if you also tried redshifts of between 0.2 and 0.4 or something, because it seems like you might have scope to work with them as well.
I agree, yeah. So I don't think we were anticipating a redshift dependence at first, but now that there is one, that seems like fairly certain. I am interested in using more of the Sloan Digital Sky Survey data set to see if, because the spectra are so nice and so resolved that testing with a little bit of higher redshift might help us with our calibration.
Right. Well, thank you, Phoebe. Let's thank Phoebe again.
Thank you.
Next, we're going to hear from Nadia Qutob from Georgia Tech, who's going to tell us about simulations she has used to understand how AGN feedback affects star formation activity.
Good afternoon, everyone. My name is Nadia Qutob. I originally hail from Georgia Institute of Technology, but I've been here this summer working under the advisement of Dr. Razieh Emami and Dr. Kung-Yi Su, studying the tracing of active galactic nuclei jet feedback through the different ionization states of Milky Way mass galaxies. My project specifically aimed to answer the question of quenching. Quenching refers to the stage in a galaxy's evolution wherein star formation stops. But in order to understand quenching, we first have to understand what causes star formation to begin with. You can see in this diagram here on the right an example of a galaxy here at the center, surrounded by a hot interstellar medium. And surrounding the interstellar medium is the circumgalactic medium, which is very cool and very sparse. When the circumgalactic medium exerts cooling flows onto the hot gas within the interstellar medium, it causes it to slow down and condense, thus forming stars. The way that star formation is stopped or quenched means that the energy within the interstellar medium needs to be enough to counterbalance the cooling flows of the circumgalactic medium. One of the prevailing theories for how this is possible is the active galactic nuclei jets that you see protruding out of the galaxy here. That was what my project aimed to study. Now, in order for these jets to exert enough energy in order to counter this cooling flow, they need to meet three key criteria. They need to have a wide enough jet cocoon, essentially meaning that they're big enough. They need to have a long enough cooling time. If they're too short, then that means they'll burn themselves out too quickly and they won't successfully quench the star formation. And they need to have a comparable energy flux to the free fall flux of the cooling radii, which essentially just means that they need to be powerful enough. The energy needs to be enough in order to counter the cooling flow surrounding it in the CGM. You can see here an example of a simulation of what these AGN jets would actually look like. And this is the type of simulation that I analyzed for my project. Now, this theory of AGN jets quenching star formation is further reinforced by observational data that's been gathered by things like eROSITA, the Chandra X-ray Telescope, and the Hubble Space Telescope. Specifically, we've been able to observe these hot thermal bubbles that emerge from the AGN jets of Milky Way mass galaxies. Now, we wanted to build directly upon this observational data and figure out what types of ions appear most prevalent and most easily observable within these AGN jets. That's where my project specifically came in. I wanted to analyze these simulations to figure out what the behavior would be of the gas morphology of these particular ions. I built upon previous work performed by my advisor, Kung-Yi, using the Gizmo and FIRE algorithms, and I specifically employed Trident and YT for post-processing of these different ion mass distributions. So we chose to do 3 different types of jets for this analysis. We took a precessing kinetic jet, a hot thermal jet, and a cosmic ray jet. For each of these 3, we then analyzed a high energy flux and a low energy flux version of the same jet, and we compared them all to a control simulation with no AGN jet, so a total of 7 different types. And we specifically analyzed 3 different types of ions, oxygen 8, oxygen 6, and magnesium 2. The reason we chose these ions is because they have a very wide range of ionization energies. Magnesium-2 has about 1/10 the ionization energy of oxygen-6, and oxygen-8 is about 10 times the ionization energy of oxygen-6. So we had a nice high, middle, and low point that we could then compare things to. This plot that you see here maps the mass density distribution of each one of these ions compared to the radius from the center of the galaxy. This dashed line that you see in the middle is specifically depicting the approximate boundary of where the galactic disk is. Everything on the left is inside the disk where star formation is more likely to take place, and everything on the right of the dashed line is outside of the disk. We see a couple of interesting trends here. With magnesium-2, we notice that it's very concentrated within the disk, but as we leave that disk, we start to see magnesium-2's density taper off. But for this magenta and this blue line here, depicting the cosmic ray jets specifically, we start to see an uptake in the mass density of magnesium-2 as we reach farther radii. For oxygen-6, we see that there's not too much interesting activity between the different types of jets until we get right about here, where you can see there's this dramatic dip, but only for specific types of jets. That correlates to high-energy jets. High-energy jets tend to see a dip in the density of oxygen-6 compared to lower-energy jets, which tend to have more oxygen-6. And then oxygen-8, we see a lot of differentiability between the jets. This is really good. Oxygen-8 tends to behave differently in every type of jet that we analyze. That makes it a very good control so we can look at how the different jets are behaving with respect to one another. And this is just another diagram depicting approximately the same thing. While the past one was comparing the ion density distribution to itself, this is comparing the ion mass density distribution to all different types of atoms within the galaxy. And this is where the behavior of oxygen-8 really starts to shine, where we can see that each one of these lines corresponding to a different type of jet are very far apart. There's a lot of distinguishability between the behavior of the different jets. Now, those two-dimensional plots are great and all, but they tend to negate a lot of the detail. We don't get to see a lot of the morphology of the jets themselves, and we don't get to see how the galaxies evolve throughout time. So I specifically analyzed three-dimensional simulations of how these different AGNs behaved. So this is just an example of the Cartesian coordinate system that I used, wherein for each one of these post-processing analysis runs, I looked at the same galaxy through three different perspectives, a face-on view and two edge-on views. So you can kind of think of it using these cats as reference, that we were looking at the same object every time, but from three different perspectives. So whenever we're talking about the face-on view of the galaxy, you can think about looking at a cat face-on. Now, this is the first example of one of the simulations that I analyzed. This is plotting a hot thermal jet here on the bottom, and at the top, a no-jet simulation. So that's our control at the top. We're not expecting to see as much activity. This specifically is a temperature distribution map. So anywhere that we see activity is going to correlate to very high temperatures. So when I run these, you immediately see a lot of beautiful activity here on the bottom, compared to the top, which is our control. We don't expect to see as much. Now, there's a couple of key details I want to draw your attention to on the bottom. You'll notice here at the middle, we're seeing the actual thermal jets themselves protruding out of the top and bottom of the galaxy. That's really cool. The AGN jets are going to be very hot. The particles are going to be moving very fast, so they're not going to be very dense. So it's really only in these temperature distribution maps that we're able to see that behavior so clearly. We also see something really interesting if you look at the bottom plot for the face-on view. Everywhere that we see blue correlates to very low temperature, but very high mass density. Everywhere that you see the very dark, bright red is very high temperature. So you notice there's this hole that's emerging at the center of the galaxy. That correlates to where the AGN jet itself is protruding out of the galaxy. It's creating these very high temperature regions that we're able to see on these temperature maps, and surrounded by the galactic disk, which depicts as being very cool this dark blue region here on these plots. This is very interesting from a temperature perspective, but now we're going to look at some mass density plots. Now this is where things get really fun. This is a plot of what oxygen-8 is doing, specifically a mass density distribution different from the last one that was showing temperature. Here we're looking at how the mass density of oxygen-8 is behaving between a hot thermal high energy jet at the top compared to a precessing kinetic jet with low energy at the bottom. So two very different types of jets. you'll immediately notice the top one is showing a lot of activity. You get this beautiful cloud of how oxygen 8 is protruding out from the galaxy as soon as we start. And as we get further into the galaxy's evolution, we can see that hole that we observed in the thermal projections emerging here as well. Now, the reason that this is blue instead of red is because this is again depicting mass. So whenever we see this hole right at the center, that's depicting a region of very low mass density. So oxygen 8 isn't able to sustain itself within the jets, but it is able to sustain itself in the disk and surrounding the disk. Now, very interestingly, on the bottom, we don't see that hole. Now, this doesn't mean that the jet isn't there. The jet is still coming out of this projection, but we're not seeing the hole. That means that oxygen 8 is still existing even within the jet. It's not ionizing, it's not being pushed out. So this is really interesting because it tells us from an observational standpoint, if we're looking at an AGN jet and we're able to see oxygen 8 within the jet cavity itself, using this data, we can narrow down what type of jet we must be observing. We can immediately say it's more likely a precessing kinetic jet with low energy flux than a hot thermal jet with high energy flux. And this is the kind of behavior that we could really only observe out of oxygen 8 because it has a very high ionization energy, so it's very difficult to break down. Next, we're going to look at a distribution of what magnesium-2 is doing specifically in cosmic ray jets. At the top, you see a high-energy cosmic ray jet, and at the bottom, you'll see a low-energy cosmic ray jet. Now, magnesium-2 shows some really interesting activity. You'll notice on the bottom, with this low-energy cosmic ray jet, magnesium-2 tends to be constrained within the disk, but it's much more sparse. It's a little fuzzier, if that's a good word for it. Whereas at the top, magnesium-2 is much better constrained. We get a very, very clear image of where the magnesium-2 is occurring. This is because magnesium-2 is a very low ionization energy. When it's exposed to too much energy, it ionizes and becomes magnesium-3, so it won't show up in these mass density distribution plots. Now at the top, the fact that we're able to get such a clear view of where magnesium is only able to sustain itself within that cool, dense galactic disk is really useful to us because it means that if we're looking at a high energy cosmic ray jet, we can use the behavior of magnesium-2 to get a very clear image of where the galactic disk begins, where the galactic disk ends, and where the AGN jet itself begins. It essentially serves as a map for us of what these different jets are doing. And last but not least, we're going to look at oxygen 6. Now you remember from this plot earlier that oxygen 6 tends to show a bit more distinguishability between the high energy jets versus low energy jets. So we're looking at a comparison of, at the top, a precessing kinetic jet with high energy flux, and at the bottom, a precessing kinetic jet with low energy flux. So the same jet with different energy fluxes. And when we run this, we notice that at the beginning, we see a lot more activity at the top, but as we get further on, we see these regions of dark blue at the top and the bottom of this simulation. The dark blue correlates to a very low mass density, as in there isn't a lot of oxygen 6 there. But surprisingly, on the bottom, we see almost the opposite effect. Oxygen 6 is kind of all over the place. It occurs within the galactic disk, it occurs a bit within the jet cavity, it's much more active. This is really interesting because oxygen 6 was specifically chosen because it has kind of a middle ground for its ionization energy. That refers to the amount of energy it takes to turn oxygen 6 into oxygen 7. And when it's oxygen 7, it won't show up here anymore. Now, the fact that we can compare two identical jets with different energy states and see so clearly how oxygen 6 behaves differently means that we can use the behavior of oxygen 6 to measure the type of energy that we're observing within these AGN jets. So we know that for the top simulation, it's extruding too much energy and it's going to ionize oxygen 6. We won't see as much of it. But at the bottom jet, it has low enough energy that oxygen 6 is still able to sustain itself without being ionized. This is something that we weren't necessarily expecting to see, but we were really excited to see because it means that oxygen 6 would make a really good control to see what type of energy and how high of energy we're observing in different types of AGN jets. So the next stages of this project are we want to specifically analyze more types of ions that we think would be easier to observe using things like the JWST. Now, we observed oxygen 8, oxygen 6, and magnesium 2 specifically because of their ionization energies. We weren't necessarily targeting things that would be easy to observe. But iron 2 and calcium 2 are easier to pick up in the infrared, so they would be much easier for things like J2ST to be able to detect. And we want all of this to translate directly into observational data. So those are the next stages of the project that I want to continue working on. So what we've learned today is that AGN jets are the most likely cause of galactic quenching. We've seen how these jets can behave, and I've specifically analyzed what types of ions are going to appear most prevalent in which types of jets, and more importantly, how those ions are going to behave, and how we can use the behavior of these different ions to analyze different types of jets. Thank you. Do you guys have any questions?
Thank you, Nadia. We have time for some questions.
So are you guys, or have you already like compared like these results to like observed data, or is there like lots of doing that?
Not yet. That's kind of the next stages. What we did so far was specifically targeting this like high energy ion, middle energy ion, low energy ion, was more just to gain a map of the terrain. So that way we could kind of figure out what we're working with and what types of trends we expect to see. All of the simulations that I showed here were just that, they're simulations. So we haven't gotten to the stage of comparing to observational yet, but we're hoping that that's going to come very soon, which is specifically why we've chosen iron 2 and calcium 2 to be the next ions that we analyze.
Have you extended or thought of extending this whole modeling to much higher energy jets,
Absolutely.
as in blazars?
I don't know if we've had a conversation about blazars specifically, but we do want to create a greater variety of the types of jets that we're analyzing. We know that just high energy version of one jet, low energy version of another jet is also a bit of a constraint. We really want to analyze a greater variety of the different energies within each jet category we chose, and we would like to expand to more jet categories that we specifically believe can meet that criteria to quench the galaxies themselves.
So,
Jonathan has one.
Yeah, well, as I say, so what you've been calculating, as I understand it, right, is the densities of the atoms in particular ionization states.
Yes.
And the fact that you have, say, twice as much oxygen 8 as oxygen 6 doesn't necessarily mean that the oxygen 8 emission line is going to be twice as bright.
Exactly.
As oxygen 6. So the next step then is to take this physical model and turn it into a spectral model.
Exactly.
So I wonder if your existing simulations do that, or whether that's another step that you still have to go.
No, that's the next step. And it's also part of why we wanted to specifically aim for iron 2 and calcium 2, because we could now take the data that we've gathered and say, all right, how do we get this emission spectra for oxygen 8? But we thought that it would be more fruitful to specifically target ions that we know we're better at analyzing, especially using the types of detectors that are available. Which is why we thought that instead of going the route of trying to figure out the emission spectra of the 3 ions I already did, instead we want to switch gears and focus on specific ions that we think would be easiest to get the emission spectra of.
Yeah, okay, that makes sense. Thanks.
Yeah.
Nice job, Nadia.
Yeah, no, we're not expecting that, okay, now we'll just point the telescope up and we'll go look for oxygen 8. We know that that's a problem in and of itself. So we're specifically going to target ions that we think are feasible with the tools that we have available.
So I had a comment and a question, and I think maybe my question was partially answered by what Jonathan said. So my comment is, it seems like your experimental design is clever because you've geometrically chosen the energy levels that you're probing in the simulations by factors of 6 and 8, or
Yes.
something akin to that.
Something akin
or
to
maybe
that.
10.
It's roughly 10, give or take.
Okay. So I understand that when you are describing the holes which are reflected by the blue color,
Right.
that's not necessarily reflecting a deficit in star formation in mass, is it?
No.
Okay.
So we do still see a high mass concentration within the disk,
I
but
see.
whether or not the 3 particular ions that we were analyzing appear within the disk was a part of the question. So we do know that there's a high mass density concentration of, actually, I think I have an extra slide that might explain this. Oh, can I show a skipped slide? Will that work? Yes, haha. All right, so this is a plot specifically of the overall mass density distribution. So not any particular ion, just all of the atoms within the galaxy. And it's comparing a high energy jet at the top to a low energy jet at the bottom. So we still see, especially these very dark regions, there's a very high concentration of overall mass when we're in the disk. Now, what particular type of ions and what types of atoms in general we're observing, that we would have to, as Razieh has put it, analyze the entire periodic table to get a map of everything. Yeah. Oh wait, did you get to your question or did I just comment on your comment?
That was great, thank you. All right, let's thank Nadia
Oh.
again. Oh, sorry.
Jonathan has one more.
Not a question, but merely want to pass on the various congratulations on YouTube to both you and Phoebe, and also note that the Segovia family is sending its best wishes.
Aww.
All right, let's thank Nadia again. Okay, and next is Brigette Vazquez-Segovia from UCSD, who's going to tell us how she has gleaned a boatload of information from a bizarre X-ray spectrum of a bizarre object.
Okay. Thank you for that introduction. So today I'm going to be talking to you about constraining the physical conditions in active galactic nuclei. Specifically, I'm going to be focusing on NGC 3227. But before I get started, I really want to thank my advisors, Priyanka, Chakraborty, and Adam Foster. It wouldn't have been a great of a project if it wasn't for them. So yeah. Okay, so I want to introduce you all to the different components that build up an AGN. So on the left-hand side, I am showing you one of the most famous images of active galactic nuclei. So in the center, we have a supermassive black hole. Surrounding that supermassive black hole, we have an accretion disk. And afterwards, we have an optically thick torus that surrounds that. We see these beautiful jets shooting at the top and bottom, and these sprinkle of clouds that surround that AGN. On this right-hand side, I am emphasizing something that we call an absorber. It is also known as a warm absorber, and it ranges in temperature something at approximately 10 to the 6 Kelvin. So we're talking really hot clouds. So absorbers are typically, they are found in between the observer and that X-ray source that you have. So sometimes they can portray themselves as absorption features in your spectra. Before I proceed, I really wanted to emphasize the beauty of this project and why we care so much about AGN. So in this video, I am quickly showing you once again what an AGN looks like. So in the center, we have a supermassive black hole surrounded by an accretion disk. We see this nice optically thick torus and the jets that shoot out from the top and bottom. Those jets are traveling at 99.9% the speed of light. So this system put together, it's just incredibly extreme. As you can see, I really wanted to emphasize the beauty of this system. With that being said, I want to talk to you a little bit as to why we ended up choosing NGC 3227 to be our target galaxy with its AGN to study. So NGC 3227 is a nearby Seyfert galaxy. Its redshift of 0.003859 makes it relatively close to us, so it's a lot brighter in our sky, and it is way easier for us to study it compared to other AGN. It's been said to have this thing called a varying ionizing continuum. An ionizing continuum tells us how different elements have different intensities and how much of each element can be present in that central AGN. In this image, I am showing you NGC 3227 with its dwarf companion, NGC 3226. Okay, so in order to understand a little bit more about what makes up the AGN that is found inside this galaxy, I will be focusing on two things: column density and an ionization parameter. So the column density is the amount of matter along a line of sight. So you can think of it as the thickness of the material that surrounds that AGN. As for the ionization parameter, it is the ratio of number density of ionizing photons to the number density of protons. So you can think of it as the degree of photoionization in AGN. So astronomers usually use two main ways to try to understand the physical conditions in these AGNs and figure out those two parameters. The first one is to look at the spectrum and try to fit a model to it. Once you fit a model, you can input certain parameters and end up getting more detailed as to like what you would end up having for your column density and your photoionization parameter. So in this image, I am showing one of the X-ray data for our observations. In the x-axis, I have wavelength, and in the y-axis, I have counts of those photons per second per angstrom. Another way that astronomers use to try to identify that column density and that photoionization parameter is through spectral synthesis models. What a spectral synthesis model does, it takes what you already know about that spectrum, and then you can input certain elements, and it kind of like recreates what you expect to see in your spectra. So for this project, we ended up using the low energy transmission grading X-ray spectra. We used it because of its high resolving power, and we wanted to retain spectra with resolving power 100 or higher. So our spectral coverage was between 5 to 160 angstrom. Here I am showing the 3 different observations that we used for this project. Another thing that I wanted to point out is that NGC 3227 with its AGN has already been studied in the high energy transmission grading at a different time period than shown here. So we're sort of filling in the gaps as to what we know for this AGN. So when we went ahead and opened our spectra, we very soon realized that we didn't have any clear absorption or emission features. So here I am showing the X-ray data. Once again, we have a wavelength in the x-axis, and I have counts of the photons per second per angstrom in the y-axis. And because we didn't see any clear absorption or emission features, that sort of gave us a hint to try to take a different route. But before I go there, I really want to show you guys the top 4 quote-unquote best fits that we could make for our spectra. So in the top, I am showing more complex fits. Here we have a photoelectric absorption component, so that takes into account anything that's between us and the source, so anything such as like dust in space. And then we have an accretion disk, a simple photon power law, and a Comptonized black body model. Both of these contain those fitting models, but this one has the addition of a reflection coefficient. The bottom 2 are a lot more simpler. These 2 just have simple photon power loss applied to that photoelectric absorption. But one common feature that I really want to point out is this specific problematic range. So for some reason, the data and model response files were not mimicking each other. The feature, we believe it to be in the LATG response file. So we simply cannot model it. We expect to see a dip there, but we don't. So with all of that being said, we ended up using that second route and taking that spectral synthesis model route to try to model what we expect to see for our column density and our photoionization parameter. So we use this thing called Cloudy, which is a spectral synthesis model. And what Cloudy does, it takes a spectral energy distribution with the addition of specific element lines of interest. So anything that we expect to see in the AGN between 5 to 160 angstrom. And it outputs a combination of that photoionization parameter and that column density, And it tells you with what intensity you expect to see those lines for that specific element in your spectra. So in order to find that ionization parameter, we had to make some certain assumptions and constraints. So what we did, we used our signal-to-noise ratio to determine a desired line-to-continuum ratio of 0.1. So here I am showing once again the same data that I showed before, but I'm zooming in. And our signal-to-noise ratio was of approximately 0.15 for all of our different points. And if I get a line-to-continuum ratio of 0.1, that means that if I were to have those elements in my spectra, they can hide inside of my signal-to-noise ratio. Here, I am showing you the emission line intensity as a function of that ionization parameter. I am pointing out the 33 different elements that we expect to see in that range between 5 to 160 angstrom with the addition of hydrogen. And I have labeled the top 10 most intense elements. So I have the ions and the angstrom wavelength. So in the x-axis, we see that photoionization parameter. And in the y-axis, once again, we have that line-to-continuum ratio. One clear trend is that as we increase that photoionization parameter, we expect to see a much larger line-to-continuum ratio. What this means is that if the data from my AGN has a high photoionization parameter, the intensity for which I see those lines would be much more prominent. So here I am showing you the top 2 most intense elements that we found. So I have oxygen 8 and iron 18. And once again, this is the output that Cloudy was able to provide me with. So I have that photoionization parameter in the x-axis, that column density in the y-axis. And these lines, these contour lines, show you how much of an intensity we expect to see those lines with in our spectra. So for something like oxygen 8, we expect to see a photoionization parameter of approximately 1.2, whereas if I were to be looking for iron 18, it would probably have a photoionization parameter of approximately 2.5. So we ended up choosing oxygen 8 to be the one that helps us determine that photoionization parameter. So here I have labeled that, so we choose to have our photoionization parameter to be less than or equal to 1.2. And that is because this can help us, once again, hide those elements. So if I were to have oxygen 8 in my spectra, and I choose this constraint of 0.2 for my photoionization parameter, it can hide inside of what I see in my data. So now I have explained to you how I was able to find this photoionization parameter, but clearly I still have not thoroughly constrained that column density. So keep in mind that's still in the log scale. So we have something like 10 to the 21 ranging all the way to 10 to the 24. So how can we constrain this column density? The very first thing that we did, we fixed that photoionization parameter to be 1.2. Then we tracked the degree of absorption for column densities between 10 to the 21 and 10 to the 24. So 10 to the 21 and 10 to the 24 are typical values for AGN. And then we used a line outside of that problematic range that I talked about earlier. So anything that ranged between 16 angstroms to 50 angstroms that I circled in those spectrum fitting models. So we ended up using iron 18 because it lied outside of that range. So we ended up getting a value of approximately 10 to the 21.6 for our column density. In this image, I am showing wavelength and 1 minus that degree of absorption. Once again, we're looking specifically at iron 18, and we ran the simulation using Cloudy, and having like different values for that column density. But if we have something like 10 to the 21, we're able to recreate that 0.1 absorption feature shown here in blue. Whereas if you see that if I increase my column density to something like 10 to the 24, that absorption feature becomes much more prominent. And if I were to have a column density of something like 10 to the 24 in my spectra for my specific AGN, then we would be able to see that iron 18 line, which we don't see. So lastly, we compared our values to what was already previously studied for this specific AGN. Here, you can see that that photoionization parameter in the bottom is relatively similar to what has been previously detected. I also was able to find that luminosity value for that AGN, which is approximately 2 times lower than we expected to have. But when we go ahead and look at that column density, we have something like 0.4. Compared to the other values, I don't know about you, but I think it's relatively low. But yeah, so given what we see for that column density, we sort of proposed a new question, and now we're thinking that perhaps we could have caught that warm absorber in a transitioning state. So from before, I mentioned that warm absorbers can manifest themselves as absorption features in your spectra. We didn't have that in our spectra, but perhaps there's a correlation between that phenomena and this specific column density. So in conclusion, we used a spectra simulation model called Cloudy. We found a column density of less than or equal to 10 to the 21.6, which can be considered optically thin. We found an ionization parameter of approximately less than or equal to 1.2. And for our future work, we want to study other multi-wavelength measurements made in the same time period. So anything at around 2009, but maybe in the UV range. Yeah, so with all of that being said, thank you very much. And
Thank you very much, Brigette, for a great talk. We have time for a couple questions.
So sorry for the Cloudy. So before the Cloudy, you showed a spectrum, like this, the X-ray spectrum. How do you constrain the Cloudy model from your observation, like observed X-ray spectrum? Does that make sense? Like, do you somehow use the data that you have to constrain the Cloudy?
yes. Okay, so Cloudy basically needs 2 main inputs. I can tell it the spectral energy distribution. So this is actually, if you look at that, that's from 2016. So this is for my specific AGN at a different time period. So it takes that spectral energy distribution, and then you can also tell it specific element lines of interest. So we went ahead and we sort of like looked through other literature to try to see what we expect to see, and anything between 5 to 160 angstrom. We fed those into Cloudy, and then that Cloudy itself runs a bunch of simulations. And you can also tell it, run this through specific parameters for your photoionization. You can even go in the negative numbers and also run it for that column density. And once we have these combinations and the different kinds of intensities for which we expect to see the elements, then we can say, because we don't see any elements in our spectra, something like this, then we have to fall inside of this range of that signal to noise ratio. So that's where that line to continuum ratio of 0.1 comes from. Yeah. Yeah.
So can you please go to the final table that you compare your work with?
Yes.
Yeah, specifically about the NH, actually the second column, could that be associated with the changing look AGN? Because it could be that there is some time variability in which you go up and down. So have you checked out whether your AGN system is kind of like a stable, or could that have some time variability? And that would be a perfect discovery just to show that,
Yeah, great question. So actually, we haven't gotten in the deep details in checking whether it's a time variability system, but I have read through just different papers that some people believe that the simple interaction with NGC 3226 can also cause some certain perturbations in the system. I'm not sure how close that is or with what magnitude, but that could certainly be a cause.
I have a question.
Yes.
Since you put this very table up that I was going to ask about, you had mentioned specifically that you chose the LETG data to analyze, and I'm wondering if your analysis is the only analysis represented in this table based on the low energy transmission grading.
Great question. I believe so. So this table comes from Mao et al., and I believe they use the high energy transmission grading. So this is a different energy wavelength. So yeah, it would be the only one using the low energy transmission grading X-ray spectrum.
So potentially that could introduce
Yes.
a systematic in either
Correct.
analysis. Yeah.
Yeah.
Yeah. We have time for one more question.
I'll make you go all the way back to the beginning when you showed a picture, like a schematic of what AGNs look like. So you showed there's a warm absorber, and then there's also a torus. So I'm wondering if you can remind me what the warm absorber is and whether the torus can also do that. If that makes sense.
Yeah, good question. So even just like looking at it through here, it could be kind of difficult visually to tell whether you're looking at a warm absorber or a torus. The main difference is that the torus ranges in temperature, so it's something like 1500 Kelvin, whereas your warm absorber, we're talking 10 to the 6th Kelvin, so like a million. So it's a lot much hotter in temperature, still warm for us X-ray people, but yeah, so that's the main difference. And also the warm absorber is said to typically lie in the mouth of that AGN. So anything that's like here, so it would be like the mouth of the AGN. Oh, the pointer. Yeah.
All right, well, let's thank Brigette again for a great talk. We're going to take a short break and we'll reconvene in 10 minutes for the concluding session of the day. Thank you, everyone.
No, you were too good. I was like, I can't go after this. That's nerve-wracking each time. I know. Oh, it's because I told everyone watching. I was like, everybody come watch.
Lots of YouTube comments. There you go, Brigette.
Thank you. I was so nervous at the beginning. I think I was talking much fast. And then I was like, let's calm down. I guess so. Now I'm like,
We. Great, Jamar.
I'm doing experiments.
Okay.
On the ball. Well, welcome back, everybody, to the fourth and final session of today's Summer End Astrophysics RU Symposium. Thank you all for being here. I'm honored to open the fourth session. And to begin it, we're going to hear from Jamar Kittling of Wesleyan University, who is going to describe insights that he has gleaned into the ancient history of the Milky Way system through an unusual means. Take it away, Jamar.
Okay, cool. Hello, everyone. My name is Jamar Kittling. I am from Wesleyan University. Today I'll be talking about finding the tidal stream of Leo 1. My advisor is Urmila Chadayammuri. I also worked closely with Fabia Bakuchi, Yunya Ni, and Anna Banaka. And let's get started. So I have a little question for you guys to start off. What is the coolest object in astronomy? No guesses?
Dark matter.
Well, Phoebe got it. It is actually black holes. So we know a decent amount about black holes. They're pretty cool. There's this class of black holes called stellar mass black holes. We know they come from a supernova, and we can detect them using X-ray. They detect them in X-ray binaries. But there's also another class of black holes called supermassive black holes that reside in the center of most galaxies. And when we try to find out where exactly they came from or how they form, it's a little bit of a mystery there. We don't really know a lot. However, there's this handy-dandy relation that we discovered empirically that relates the black hole mass of the supermassive black hole with the velocity dispersion of the bulge of the galaxy. And someone may ask, like, oh, why does that matter? Well, the velocity dispersion of a galaxy bulge, the bulge of the galaxy, can be related to the stellar mass of that bulge. What that implies, that gives us this MM* relation, which relates the black hole mass with the stellar mass. And what that implies is that there's a coevolution between the bulge of the galaxy and the black hole. So essentially, the bigger the black hole, the bigger the stellar bulge of the galaxy. So this implies that there's some sort of physical mechanism in which both the black hole and the bulge of the galaxy both form. And that's pretty cool. So if we try to test this theory out with our own galaxy, we have the Milky Way. It's pretty big, it's a pretty normal galaxy, has a lot of stars. Its black hole is kind of puny, but if you put it in the MM* relation, it still fits snugly within that scatter, and everything's all good. However, if we look at another galaxy, Leo 1, Leo 1 is a dwarf spheroidal galaxy. It is a satellite of the Milky Way, discovered in 1950. It's pretty far. It's one of the most distant Milky Way satellites. However, it was quenched 1 billion years ago, and it's pretty puny. Not a lot of stars in there. It's not pretty massive. It's a really small boy. But if you look for the black hole, one group called Bustamante-Rossel et al., they discovered the black hole is at the same magnitude as our very own Sagittarius A star, the Milky Way's black hole. So we have this gigantic black hole in Leo 1, and we try to put it in the MM* relation. It doesn't really fit well. So we're left with this question, right? If supermassive black holes co-evolve with bulges, and Leo 1 barely has a bulge, where did that black hole come from? And you know, it's a little mysterious. But we do have an idea. Essentially, our hypothesis is that the bulge was there, but it was removed by a process of tidal stripping. Tidal stripping occurs when we have a large galaxy and a small galaxy. As a small galaxy orbits a large galaxy, the tidal forces exerted by that large galaxy tends to strip the stars from the smaller galaxy. So as the star orbits, it leaves behind this stream of stars that we call a tidal or stellar stream. So we believe that this is what happened, and we have a grand plan. We have a mission to how we can test this theory. So the first step is to get the current orbital parameters of Leo 1, using current day modern technology. With this current stuff, we can use these properties to infer the past properties of Leo 1 using this Python package called Galpi. So basically find out how Leo 1 looked when there's dinosaurs walking around. From this, we can use a software called Arepa, which is an n-body simulation, to run from these past conditions back to the present day. So we're going back to the future to find out where Leo 1 is today. And finally, we're going to use the result of these simulations to look for stellar streams in Gaia data. So, past Leo 1, also pretty mysterious. There's a lot of things we don't know. Importantly, we don't know where it was or how it was moving, basically its position and velocity back in the past. We also don't know a lot about its mass, how much stellar mass was there, how much dark matter mass was there, what was this halo looking like. Actually, where was the stars? Was it distributed in a disk, a halo, a bulge? We don't know a lot about its morphology, if it was a spiral or just elliptical, stuff like that. In addition, we don't know if dynamical friction would have affected the galaxy, in which, as it orbits the galaxy, the Milky Way dark matter halo will slow it down enough to significantly impact its orbit. And we don't even know when it would have been stripped. Like, at what time would have most of the stars of Leo 1 been stripped from it? But these are a lot of questions, but we have this nice tool to help us out with at least some of them. And it's called Galpi. So Galpi basically uses potential theory to model the gravity of the Milky Way or any sort of complex object in terms of like potentials, analytical potentials. For example, it takes the Milky Way, it decomposes it into 3 separate components, the bulge, the disk, and a halo. And for each of these, it assigns to it like an analytic function that expresses its potential. And with this potential, you can calculate the gravitational force. In addition to this, it also has a nice feature where it can go to use this astro query to retrieve values of its initial conditions from Sinbad and then puts it into this orbit object. So if you take this orbit object that has initial conditions and integrate it in some potential, such as the Milky Way potential, you can get this handy-dandy orbit. If you want the details on how it defines the Milky Way potential, you can go to Bovee 2015. But the most important part about that is normalized such that the sun is 8 kiloparsecs away from the center of the Milky Way and is traveling at a circular velocity of 220 kilometers per second. So with all measurements, you're going to have uncertainties. Because galaxies have a really extended and antisymmetric mass distribution, any orbit within a gravitational potential of a galaxy will be inherently chaotic. So this means that if you change any parameter within the initial conditions of like Leo 1 and you try to integrate it, it'll be widely different if it like varies by just a little. To take this into account, we took all the parameters, the positions and the velocities of Leo 1, and we changed them just a little bit. We randomly sampled them, assuming that they're a Gaussian distribution, and took those values and also integrated those through time to see how it affects the orbit. And this is what these plots are. So the best fit orbit, like the classical orbits you get, the classical values you get from like Sinbad, that's the dark dashed line, while all the gray lines are the sampled random parameters that we integrated through time. You see that the distance is pretty well constrained. That just has to do with conservation of energy. But if you look at this plot, which is the X and Y plot, it's basically looking face on at the Milky Way disk, similar to what Nadia was saying. We can see that it starts over here, but the minute it goes past the pericenter of the Milky Way, the orbit becomes very sprayed out, and it comes to this like wide distribution. So this is a really important test because we don't really have like a good idea of where Leo 1 was. We also tested this idea with dynamical friction. We can see that the blue line is similar to the line before, but we also used it using dynamical friction, using the potential objects. And we can see that the orbit doesn't really change that much. It's still within this scatter, so we decided to ignore it after this point. Lastly, we want to find out when tidal stripping would have occurred. So we have this Milky Way potential object. We also can create a Leo 1 potential object, make it something simple like an isothermal sphere. If we put a star at a certain distance away from the center of Leo 1, we can calculate at what distance Leo 1 has to be from the Milky Way such that that star becomes stripped. And that's what this plot is showing. Each line represents the distance that star is from the center of Leo 1. The x-axis is the mass of Leo 1. And you can see generally as the stellar mass of Leo 1 increases, the Leo 1 has to be closer to the Milky Way for that star to be stripped. So we take those values, and if we plot them on the orbit of Leo 1, we can see that most of the stripping would have occurred at 2 billion years ago. So with that estimate, we decided that the best starting point for our simulation, our red plus simulation, would be around the 4 billion years. That's to catch all the effects. So I decided to set our T0 to 4 billion years in the past. So now we have a picture of the past Leo 1. Our starting point is 4 billion years ago, and we want to run a buttload of simulations to catch the entire parameter space here. So essentially, we have 10 simulations where we vary the initial orbital parameters, which is the position and the velocity. We also want to vary the stellar mass. We predict the stellar mass assuming that it's on the M star relation. However, there's still some uncertainty related to that. So we varied that across 1 sigma. We also want to vary the disk to bulge mass ratio from like 5% to 95%. So basically from disk dominated to bulge dominated. So we have 5 simulations on that. And we also have 6 simulations where we varied the actual disk size. So we have 3 where the disk size is varied in a disk dominated system, and 3 where the disk size is varied in a bulge dominated system. So here's a quick little movie for you guys. This is one of the results from our simulations. This is a result where we varied the initial orbital parameters. We see that as Leo 1, which is like all the red stuff, passes by the Milky Way disk, which is the blue stuff, it does kind of get tidally disrupted and kind of swooped around and becomes this wide distribution of stars. And this is really promising in our theory, because this suggests that even if at this very small initial mass for Leo 1, stripping still occurs. Here's another movie. This is the movie assuming that Leo 1 is on the M star relation. So if we look at this, you still see that it still gets stripped, which is pretty cool. I enjoyed that. So this is the plot of stellar positions as they will be today, as predicted by simulations. You can see that it has basically this cool butterfly effect. This color ball shows the distance, and you can see that most of the stars today fall at the same distance Leo 1 is today. In addition, we can see that the predicted position of Leo 1 is pretty close to the actual position of Leo 1 today. So all this is pretty promising. This is where we varied the orbital parameters. And this is where we just varied the stellar mass. And it's decreasing from, left to right? So yeah, we can see these results, and we think our simulations are working pretty well. With these results, we have some next steps. Number 1 is to run some more simulations. Number 2 is to move on to instruments to test these simulations, look for these stars using instruments such as Gaia, or even BioSpec, or even upcoming instruments such as ViaSpec. And lastly, we hope to see the stream, and even if we see the stream, we hope to constrain Leo 1 based off the parameters we used in our simulations. And yeah.
Thank you, Jamar, for a great talk. We have time for some questions, and I see some hands. Want to go ahead and...
Yes, it was a great talk. So I was wondering, it's very interesting, this hypothesis, right? And if you go back to that plot of black hole mass versus galaxy mass, something like that, do you think that if you, from your simulations or as much as you can tell, if you take into account the difference from where it should be, this galaxy, to where it is, and you compare it to where the Milky Way should be, because the Milky Way mass should be bigger than we expect, right? If this is the case, if it's stripped it, does that make sense in that plot?
Oh
Do
yeah.
you see what I mean? I'm not asking this question very well, but if you just take those into account, do you think these things would align well?
Hopefully. Well, in a simulation, we used a model of the Milky Way, so we're not really like looking at the Milky Way too much, because that's kind of outside the scope of our project.
Okay.
So,
Yeah.
yeah.
Okay. This is super cool. Super interesting.
I don't know much about this process, so I'm wondering, I heard that we should see star streams, but where did the other stars go? Like, did some get absorbed by the Milky Way? Are some other dwarf galaxies? Like, what happens when a galaxy is stripped like that?
Yeah, so what generally happens, we can just look at this image here. So what generally happens is that the stars just kind of like enter the halo. Like you can see like a detectable stream throughout the halo. And in our simulations, you can see that as it goes through, the stars don't really like enter the Milky Way. They more of just become a little spray. They just kind of like get swooshed out in this giant stream that you can see in the final plot.
So they might be too faint to detect.
Yes, that's a little bit of a issue.
So that answers my question. So you're not expecting these extra stars to be in the Milky Way? Okay,
Not-
that answers my question too.
Yeah.
So I know at the end, you mentioned a little bit about like what's the next step with Gaia. Could you talk about that a bit?
Yeah, so if we have position values, like if we have idea of where it is, we can use modern instruments to find out. We can look in a position and see, hey, are there stars there? So we can use Gaia, but the main problem with Gaia is that it's not really functional at that distance. It's not the best. It's not really built for that. So there's also other instruments that use this spectral data to find out if these stars will belong to Leo 1. And yeah.
I was just checking our MMT archive. Leo 1 has been done with Hector shell in MMT some years ago, but it will suffer the same problems you just talked about. It's one of the most distant dwarf orbitals, so that the only data is around the center part, and it's just the very bright stars. But it's possible to extend those observations in the future, either Hector shell or volume study, or some others.
So if it's a stellar stream, that would be huge to solve the problem. But like, are there other theories for what else could be causing the variation from the M sigma relation?
Well, the only other theory I know is that the M sigma relation is wrong. But I don't think that's entirely right. But yeah, I don't really know a lot more other theories. To answer your question.
So looking at this image, it kind of looks like the stars are distributed into like 3 separate pieces of a stream, or like how is this? How do you define a stream in this case? Like, is it like the whole curve? Like this is one stream in that case?
Yeah, I guess it'll just like depend on like if it's like an entire unit. So I would say, I mean, if you can see the distance information, you have like a good piece here that's all at the same distance. But if you see like this farther stream, you see it's like a darker shade of blue. So it's just kind of like farther away. These are probably like 2 different like structures is what I would guess. But I'm also not a stream expert, so I'm just kind of guessing.
So I had a question. It seems to me that one of the challenges you faced, but didn't, well, at least you were gracious enough not to complain about it, as I probably would have done, is the multi-n parameter space that you had to span in order to characterize the object that you're studying. And I'm wondering if there was 1 or maybe 2 dimensions of that parameter space that you found more constraining than others.
What do you mean by constraining?
Well, so here you have this multi-panel montage of basically your results. Where are the things that you're going to look at? Where this is sort of a prediction of where would you look to find the stellar streams that would tell you, that would be diagnostic of the past of Leo 1, what it used to be. And to get there, you've explored various dimensions, bulge to disk ratio, and where it was in the past, and all these different things. Did you find some of them to be more useful than others?
Oh, I see. Well, if I had to we didn't really analyze these too much in depth yet, but if I had to answer your question right now, I would say that top right panel, this one right here, the fact that the predicted position of Leo 1 today is closest to the actual position is pretty telling. It's probably showing, because in each of the other plots, you can see that there's still like a large distance because we kept the orbital parameters constant here. So if I had to constrain it, I'll probably just choose those values as the actual initial Leo 1 positions.
Gotcha, thank you. All right, well, if there are no more questions, let's thank Jamar for a great talk. And next, we're going to hear from Anya Phillips from The Ohio State University, who's going to tell us what machine learning can tell us about stellar parameters and how we can interpret stellar spectra.
So, as that lovely introduction just said, my name is Anya Phillips. I go to Ohio State University, and this summer I've worked here with Drs. Cecilia Garraffo, Josh Wing, and Phil Cargill, implementing transfer learning to improve a machine learning model for stellar parameter estimation, which I will talk about today. So, knowing the ages and masses of a lot of stars can help us all across the field of astrophysics, and my colleagues have demonstrated that very well today. So for example, ages of field stars can help us constrain the star formation history of the Milky Way, which is kind of coming at the same science questions as Nadia's project from a more observational perspective. Ages can also let us learn about streams from the Milky Way's merger history, which is exactly what Jamar just talked about. Additionally, having accurate characterizations for host stars can tell us a lot about the environment and potential habitability for the planets that surround them, kind of like 2 planets that Aislinn discovered and talked to us about this morning. So hopefully I've convinced you that this is important. However, age and mass are not directly observable when we observe stars, and so what astronomers often do instead is fit more observable parameters like temperature and luminosity to the predictions of theoretical stellar evolutionary tracks or isochrones, like the ones I'm showing in this plot of luminosity versus temperature, also known as the HR diagram. However, this method can be a little bit unreliable because you might see that these evolutionary tracks all cross each other, or they're very degenerate, particularly in certain areas of the HR diagram. And in these regions, we're unable to get as precise of age and mass estimates. Additionally, if we want to quantify the uncertainty in our parameter estimates, we have to implement very computationally expensive probabilistic methods that scale poorly as our data sets get larger. Ooh. Great. So StelNet is a machine learning model that's attempting to solve these problems. It is a collection of deep neural networks that take as inputs a temperature and a luminosity, and it outputs estimates of age and mass. It solves the problem with the degeneracy in stellar evolutionary tracks by having separate portions trained for the portions of stellar evolutionary tracks before and after the zero-age main sequence, or ZAMS. And those 2 times, like between those 2 times, are where most of the degeneracies arise. Then, once it makes an estimate with each of those separate models, it can hierarchically combine them into one estimate based on the relative probabilities of observing stars of each predicted age and mass. And finally, StelNet quantifies the uncertainty in its outputs by running your inputs through multiple neural networks for each evolutionary stage, which yields a probability distribution instead of a single best estimate. And it does all of this very quickly and efficiently once trained, so it's perfect for analyzing large data sets. However, there are still some outstanding issues. So StelNet's original training set were stellar evolutionary tracks of solar metallicity from MIST, and it performs really well in this domain, but it's not expected to do as well on real observations like the stars I'm showing in this alternate HR diagram from the real world. And this is for 2 reasons. So first, stellar evolution is not a perfect theory, and so each of its implementations, including MIST, are going to have their own systematic biases that will carry over into any estimate that StelNet makes if that's the only training data it has seen. And additionally, real photometry have observational uncertainties that offset the measurements we make from the predictions of stellar evolution theory. So, one way we can adapt StelNet for better performance on actual observations is a technique called transfer learning. in traditional machine learning, we assume that the data a model is performing a task on come from the same data set as the data the model was trained on. So for example, the green model all the way on the left is trained to perform a task on green rectangles, but if we wanted to perform the same task on orange ovals, we would have to train an entirely different model to do so. Transfer learning is leveraging the knowledge a model has gained from a previous training process, tweaking its weights and biases slightly to fine-tune its performance on a distinct but similar data set. So in our case, we'll load a baseline StelNet model that's trained only on missed isochrones. We'll retrain it for relatively few observations on relatively few new data points, which will consist of well-characterized observations. And that will effectively calibrate StelNet for better performance on real data so that we can actually use it to do astronomy. So, to do so, we're going to have to start by assembling this training set of well-characterized observations. And because I mentioned StelNet has separate portions trained for the pre- and post-SAM stars, we're going to need new data in each of these regimes to train those models separately. So to start off with the post-SAM stars, we have this catalog of BAF-type stars that have reliably determined age and masses. And when I say reliably determined, I mean the authors went through that computationally expensive process I was mentioning before to quantify the uncertainty in their age and mass estimates. So we trust this catalog. And I'll denote these stars in blue going forward. Then we have another catalog of subgiants that I'll denote in orange. And in addition to them having like rigorous probabilistic estimates of age and mass, subgiants evolve very quickly, and so we get extra precise age and mass estimates from model fitting. So another good catalog. And lastly, for the post-SAM stars, we include the Gaia FGK benchmarks from the European Southern Observatory, which I'm going to denote with yellow stars in this presentation because they're kind of considered the gold standard for ground truth stellar parameter estimates. They're very close by and very well studied, and so we want to prioritize StelNet's performance on this catalog in particular. Then for the pre-zero age main sequence catalogs, it's more a question of data availability. So a lot of pre-SAM stars in the literature exist in catalogs of open clusters. And often in an open cluster, you'll have a temperature, a luminosity, maybe a mass estimate for each star in the cluster. But most catalogs will just give you an overall age for the cluster as a whole, which doesn't work so well when you're training a model like this. But we did find two open clusters that have individually estimated ages, and those two are the Orion Nebula cluster, which I'll show in purple, and NGC 6530, which I'll show in green. Another thing to note is I mentioned that StelNet's trained on solar metallicity stellar evolutionary tracks. And so we want to keep any new training data reasonably close to a iron abundance of 0. So we keep all of this new training data having a metallicity within 0.5 dex or metallicity units of the solar value. Another note is that each of these samples have age and mass estimates from different implementations of stellar evolution theory, including and apart from MIST. And we expect that this will introduce small systematic biases in the model and that the effect will be kind of difficult to predict. So constraining the trade-offs of this method is something we should really investigate further, but for now, the idea is that by including estimates from many different models, we're training something new that's robust against any one of these systematics, even if it sacrifices precision. So then we actually implement the transfer learning by sampling about 30 stars from each of the catalogs, except for the FGK benchmarks, which I mentioned before. We want to prioritize StelNet doing really well on this sample. So we augment the data, which really means making 5 copies of each of the stars in this catalog and then sampling 50 stars from the resulting array as opposed to just 30. And then we train the model and we can evaluate how it does going forward. So starting with how it does on the post-SAMS catalogs. So the next 4 slides are all going to be very similar. So I will explain this one in detail and then go quicker through the rest of them. So these plots are just showing StelNet's prediction of a certain stellar parameter, in the case of this slide, age, and on the x-axis, the reported or ground truth value. On the left-hand side, we'll show the baseline model's performance, so that's the one that's only seen missed isochrones. And the one on the right side is after we've done transfer learning with subsets of each of these training catalogs. So in the bottom panels, you can see the residuals in the predicted and true values, and we can see that after transfer learning, the residuals have decreased, which is great. That means StelNet is learning. Additionally, we computed a Pearson correlation coefficient, which is just a metric of how well the two parameters follow a linear relationship, where values closer to 1 indicate better correlations. And we can see that after transfer learning, the predicted and true ages are better correlated. We can do the same thing for StelNet's mass estimates, where again on the left we have the baseline, and on the right we have the model after transfer learning, where again we see that the residuals decrease and the Pearson coefficient increases. One thing to note for both the age and the mass distributions is that in particular the yellow stars or the FGK benchmarks have really like the best estimates, that was our goal. So it's good that those are doing well. We can do the same analysis for the pre-ZAMS training catalogs, starting with StelNet's age estimates versus the reported value of age. On the left hand, you can see in the baseline model that below ages of about 1 million years, StelNet was systematically underestimating stellar ages, and that we've corrected for that after transfer learning, along with the same general improvement that we saw previously for the post-ZAMS stars. And then similarly for mass, where we just see the residuals decrease and the correlation get better. So that's great. StelNet is doing well on the catalogs that we drew training data from, but the goal is really for it to be very widely applicable. So we can test it further on 2 open clusters that we couldn't use for training because they didn't have those individually estimated ages, but they do have a literature value for the cluster that we can compare StelNet's distribution and age estimates to. So to give you a better sense of what I mean, these are results for the post-zero age main sequence cluster Praesepe, which is about 700 million years old. So on the left-hand side, these are distributions in StelNet's estimates of these stars' ages, where the baseline predictions are in the blue histogram, and the model after transfer learning, those predictions are in the orange histogram. The vertical red line is the literature value for Praesepe's age, and you can see that both models are significantly overestimating stellar age. Although, after transfer learning, the distribution seems to shift a bit closer to the true value. And I'm going to circle back to this after we talk about the mass, where you can see that the mass estimates are reasonably good for both models. But you might notice that most of the stars in the Praesepe cluster are less than 1 solar mass. And if you think back to this plot I showed a couple slides ago, the masses in our training catalogs were overwhelmingly greater than 1 solar mass. So it's already difficult to estimate the ages of low-mass stars since they evolve very slowly. So that, in combination with the fact that we didn't give StelNet a lot of training data in this new regime, makes it unsurprising that it's still struggling here. We can also perform the same test on the pre-ZAMS cluster NGC 2547, which is about 30 million years old. So you can see in the age distributions that after transfer learning, we've counteracted what looks like a systematic age overestimation that we saw in the baseline model, which is the blue histogram. However, we've widened the distribution considerably. And again, I will circle back to this after I tell you that both models are doing really well at estimating mass, which is good. So, but circling back to the age estimates, it can be a little discouraging to look at this wide distribution of age estimates around a seemingly very narrow, precise value for the cluster's age. However, stars and clusters don't all form at exactly the same time. And if we want an idea of the characteristic spread in stellar ages within a single cluster, we can look at the clusters we used for training that had individual age estimates. So you can see for both of these that stars within a single cluster can have ages that vary over several orders of magnitude. So if we compare that to NGC 2547, where we had ages varying from 10 to the 7.3 to 10 to the 7.9, that now seems more reasonable, and StelNet is doing a good job. So I would like to summarize. we've showed that transfer learning results in better correlations between stellar predictions and reported values of stellar parameters. We've shown that transfer learning models are performing reasonably well even on catalogs outside of the training data. Although we have highlighted that we could improve StelNet's performance on low-mass post-SAM stars by including more of these in the future training data sets. So speaking of improving StelNet, there are several avenues we can take to make it a more useful tool to astronomers at large, starting with a couple possible adjustments to the training sample. We could either homogenize the models that we use to estimate ground truth ages and masses, or we could use quote-unquote better trusted age determination methods apart from model fitting to use as our ground truth. Second, right now, StelNet takes a temperature and a luminosity as inputs, but those are already derived quantities, and we think it would be more user-friendly if StelNet could make age and mass estimates directly from photometric observations. Lastly, we could change StelNet's architecture itself, starting with implementing a way for it to propagate observational uncertainty through to its age and mass estimates, and additionally adding metallicity as an output dimension because, as I've mentioned, technically you should only be using this on close to solar metallicity stars, and we want it to be as widely applicable as possible throughout the galaxy. So with that, I'm going to go back to the conclusion slide and ask if there are any questions.
All right. Thank you very much, Anya, for a great talk. We have time for some questions.
Brigette?
Yeah, can you talk about maybe what are your hypotheses for why you see an overestimation in the mass?
Overestimation in mass, here?
Yeah, so I think there was a slide where you said you're overestimating a whole value. I think it was one of those.
Was it the ages?
Yeah.
Yeah, so I don't know if I can speak to why it's an overestimation as opposed to an underestimation, but like I was saying, so low mass stars evolve slower than higher mass stars, and so the difference in position on an HR diagram from the same time step is going to be way smaller the lower the star's mass is. So that's why we don't expect model fitting methods to work as well for low mass stars. Is this answering your question at all?
Yeah.
Okay.
Thank you.
Yes.
Maybe I missed this, but what exactly is the mechanics of the transfer learning process?
Yeah, it just, rather than loading a neural network with randomized weights and biases, you load one that's already trained on a specific data set, and then you retrain it on new data. Yeah. Yes.
The usual question regarding machine learning is uncertainties. Is there a way to derive uncertainties on your age estimates and mass estimates?
Yeah, so that's built into StelNet's architecture, which I can't really take credit for. It was already put in place when I got here. But so basically your inputs go through many different neural networks that are each trained on a bootstrap of the original MIST training data. And so then that will give you an output distribution of the different estimates that all the different neural networks made. And so you can imagine that if you're in an area of the HR diagram where it's more difficult to make that estimate, that the spread in the estimates the neural networks all make would be wider. Does that make sense? Sorry?
Yeah.
Okay. Jonathan.
Yeah, following on from that, then how computationally intensive is this? Because whenever you do that kind of method to get your errors, you're doing many more computations. So how long does it take to run one of these?
Not long at all. So neural networks are very fast. It's just a series of pretty simple linear transformations. And so that's really the benefit of using something like this over traditional probabilistic sampling model fitting methods. Yeah.
So I have a question.
Yes.
I noticed, and you pointed out, that probably helped me notice, that the FGK stars hew much more closely to zero residuals than your other training data.
Yes.
And those are so well studied, as you pointed out. And I'm wondering if that is suggesting that there may be deficiencies in the other data as opposed to that suggesting a deficiency in the method. Do you have a comment about that?
I would say that's very possible. Because like I said, these all, the blue and the orange stars have age and mass estimates from different isochrones, like different stellar evolution models. And so, let me think. I would say, yes, I would agree that it's good that we're prioritizing the FGK benchmarks, because any additional training data that we add that has estimates from model fitting is going to have the associated systematics from the models that those authors used, if that makes sense.
Yes, it makes total sense.
Okay.
Yes. And we're planning to use those same stars to help calibrate spherics. So
cool.
Yeah. So that's reassuring.
Mm-hmm.
Yeah. Okay, well, let's thank Anya again. Oh, did I miss one? I'm very sorry. Please.
It was just kind of a quick clarification question on my end, because I don't know much about machine learning, but at the beginning when you were talking about transfer learning and needing to adjust the weights and stuff, that was accomplished in your work by emphasizing the benchmark stars and adding the new sets of data, right?
I think I might have used the word weights in two different ways. So in terms of giving the FGK benchmarks more weight, that's just letting the model see those more often in training. The weights and biases are like the parameters within your neural network that are getting tweaked as you iterate through the training process.
Okay.
Yeah, I'm glad you asked that, because it might have been confusing.
Okay, thank you for the question. Let's thank Anya again. Okay, and now we're fortunate to be able to hear from Devisree Tallapaneni from Cornell University, who is going to tell us about techniques she has developed to help us cope with things that many of us have to do in bread and butter photometry astronomy all the time. Why don't you mic up?
Okay, cool. So hi everyone, my name is Devisree Tallapaneni, and I'm going to talk to you about quantifying the filamentary ISM. And this summer I worked with Andrew Sajari, Eric Koch, and Doug Binkbeiner on this project. So here is an image of a nebula with some beautiful filamentary structure. And a question we might ask is, what is the flux of a star on a particular filament? And we might also ask, what is the flux of that actual filament itself? But this is actually a pretty complicated problem because the filament is highly structured, so it's hard to decouple the two. And this is made even more difficult by the fact that the ISM is full of these filamentary regions that are so diverse. So here we're showing various regions from WISE 12 micron dust maps, and you can clearly see that there's lots of diversity, and a lot of these filaments are very directional. And oftentimes, a lot of people have been attempting to model these filaments, and the way in which they do this is they make a Gaussian approximation. And this leaves you with fields that look something like what's on the right. But you can clearly see that there's not a presence of a filament here at all. The real data looks something more like this, where you actually have a clear filament that you're capturing. And the difference between these two images is that the one on the right is Gaussian, and then the one on the left is non-Gaussian. And so it's truly this non-Gaussianity that is due to the filament. And one way that we can better model these filaments is by this algorithm that was developed by Andrew called local pixel-wise infilling. And so the question at hand is, if you have a filamentary region with a star, and we want to know what is the structure of the filament, we look to a larger local region that is outside of that specific infill subregion. We then pretend that we don't know any information about the region that is confusing to us, and then build a distribution for what the infill subregion looks like by using little cutouts of the size of the infill region and sort of pinning it across the whole image. And this helps us build a distribution for what the infill subregion looks like using samples that have been developed from the local interstellar medium. And this is what we term the covariance matrix C. And then LPI then uses this matrix and then conditions on the pixels that are outside of that masked region that you see and inside of that red cutout of the infill subregion. And so together with those two information, with the conditioning, we're able to recover the infill distribution, and we use that to generate various infills. And that's what I'm going to show here. So here we're masking out region where perhaps there is a bright source, and asking what should be there in terms of filament structure. And so the question that we really want to ask is whether this method of local pixel-wise infilling is actually recovering filamentary structure, aka the non-Gaussianity. And so the way we measure this and capture if the method is doing the correct thing is we turn to statistics as a measure of non-Gaussianity. We start off by measuring chi-squared, and then the power spectrum, and then the 3-point correlation function, and wavelet scattering transform. And in that order, these statistics capture increasingly more information about ISM structure. So the methodology that we use is that we first infill a WISE region using local pixel-wise infilling and measure the different statistics. We then generate a Gaussian random field, a Gaussian model, based off of the statistics of the WISE region. We then also infill that Gaussian field and use it as a baseline comparison of what the Gaussian approximation looks like compared to the non-Gaussian or filamentary version. And so we can look at the differences to capture if we're truly picking up on these filaments. And so I'm going to lay out the structure of the plots that I'm going to show in the next couple of slides by saying that the x-axis is going to be mainly the infill radius. This is just the region that we are infilling. So as you can see, it gets larger and larger, and that corresponds to increasing values on the x-axis. And then on the y-axis, we're going to present our statistic. So we first look at chi-squared. And here, we're looking at the real image subregion and comparing it to our local ISM-built distribution, the reminder is that as you're changing your value of the infill radius, this distribution looks slightly different because you're building it off of only the pixels that are unmasked. And so we track this across infill radius to understand if the real subregion that we're starting off with looks like our local ISM or if it looks different. We also ask the same question for the infilled subregion and wonder if the infill subregion also looks like is capturing the covariances in the local ISM or if it is different. And so we find some interesting results, and we find that in the small infill radius limit, you can clearly see that we're not infilling very much, and we're not really infilling much of the filament at all anyways. You can see that these two values really agree. And then we find that there's this interesting intermediate regime where you can clearly see that we're starting to infill the filament and picking up on some of the structure potentially there in these various draws from the distribution. And so we look at this region as the interesting region from where we hope to see these non-Gaussianity in our statistics in the next that I'll present in the next couple of slides. And then when you have large infill radius, you can clearly see that we're beyond most of the structure of the actual filament, and so you're getting larger results and asymptotic results. And we compare this to the Gaussian random field, which clearly is a lot more stable across infill radius because it's built off of that covariance matrix C that has been defined to be the same as for the WISE region. So we next look at the power spectrum, because the power spectrum measures the distribution of power across various spatial scales. So here's an example of a power spectrum on the right that has been 1D radially averaged. And this slope is often capturing information about like turbulence properties. That's usually where it comes up. And the key problem with it potentially is that it strips out phase information. So it's hard to capture some of the structures that we're interested in using it, but because different spatial structures could potentially produce the same power spectrum. And we see that here when, so on the left is the WISE region, and then on the right is the Gaussian random field. And we first note that these are the slopes of the power spectrum on the y-axis, and we note that the values are different. And we note that it's because that the Gaussian random field, the power is being shifted from small spatial scales to large spatial frequencies as the power spectrum slopes get flatter. And you can see that the slope value itself is pretty consistent across infill radii. So we next turn to the 3-point correlation function in hopes that it'll capture more information. And it should, because it measures the correlations between any 3 points on an image by capturing both information about spatial scales as well as angular orientations. And doing so, it helps preserve phase information, which is better for detecting these sort of non-Gaussian filamentary structures we're interested in. But one potential problem is that it could be significantly affected by outliers and sometimes doesn't handle local variations very well. And we notice that the 3-point correlation function, in fact, captures this information. So here on the y-axis, I'm plotting the relative value of the 3PCF, of one 3PCF coefficient. So that's the value relative to r equals 0, where we have no infill. And you can clearly see that on the left in the WISE region, we have a non-zero 3PCF coefficient. And this is really important because it's the fact that this is non-zero that is telling us that there is some non-Gaussian structure, because that's what the 3PCF coefficient is picking up. And you see that it holds true for both the small radii limit that I was talking about as well as the intermediate regime. So our infills are actually picking up on the structure that I was mentioning in the filaments. And then for the Gaussian random field, you can clearly see that the value is pinned at 0 because it's not capturing that same filamentary structure. And then as you infill more and more, you're moving beyond the scale of the filament, and so you approach the limit of the Gaussian random field. And so we see pretty similar results for the wavelet scattering transform as well, but I won't touch on it as much right now for the sake of time. So future work will include looking at distributional comparisons of statistics across many infill regions. So we've compared this for one region for right now, as I've displayed, but we can do this for lots of regions, and I've done it for a couple WISE regions, but the key thing would be to compare these statistics across different coefficient values and also across different images. And another thing we hope to do is explore different priors. So this is our referring to the local ISM covariance matrix C that we've built. And we hope to test out different ways of building that potentially by using isotropic versions and so on. And then finally, I want to leave with the fact that the ISM is full of lots of filamentary directional structures, and that directly correlates to anisotropic non-Gaussian structure, and that this method that we're using, local pixel-wise infilling, is actually capturing those filaments and non-Gaussianity. And we see this in our chi-squared metrics because it's highlighting this sort of interesting regime where we're picking up on correlations that are larger than the size of the infills. And we're also seeing this through the non-zero ISM statistics in the 3PCF and WST. And that's telling us that we're capturing this non-Gaussianity and that we're capturing the actual filaments. And then I would like to end with saying that thank you to all my advisors, Eric, Andrew, Doug, and thank you to Matt and Jonathan, and of course our RE cohort.
Thank you very much. Right, we have time for a few questions.
So in the images that you showed, you're kind of like, so there's like that black thing in the center that's expanding, right?
Yeah.
Once it expands fully, do you still have data outside, or does that like picture itself sort of represent when you reach that Gaussianity limit thing that you talked about?
Yeah, so the thing that it's doing, so let me go back to the original. Okay, sorry. So the thing that it's doing, so the black region, is we're masking out regions that we want to infill, right? And as you, like, okay, this is a slide. Okay, so the local distribution that we're using to like model the infill region is built off of like the sort of a larger region, but then the conditioning is done just using the pixels like that is within the sort of region that I was showing where the like hole is being blown out. And so when you have like, when you go to these really large radii, you have very few pixels with information that are telling you about like the structures and so on in the actual image.
So I have a question.
Yeah.
So you did your analysis, if I understand correctly, solely on the WISE 12 micron mosaics.
Yeah.
And so you perforce had to adopt an algorithm, which you're then testing the efficacy of, if I understand.
Yeah, kind of.
But there are, as I'm sure you're aware, other ways of observing the ISM and structured things with Spitzer, Roman, Hubble, that all have different scales and wave bands. And so I'm wondering, is it possible to optimize LPI for these different observatories and their beam sizes, and so that you could you pick the perfect LPI for the, is it an optimizable algorithm?
So I'm not 100% sure I exactly know what you mean, but I'm going to say what I think you mean. I think like this is like a general algorithm, so it wouldn't too much matter. Like it is not like sensitive, I think, to like exactly this. The key things you might want to tune is like the region that you're using to do the conditioning, and the regions that like you're using to build like your local, like you're using as like your local model for that initial region. So those are things you might want to tune, but I think the algorithm itself isn't, to my knowledge, like limiting in
Okay.
other ways. Yeah.
Okay, thank you. Oh.
So I thought, when you started, I thought you might be going to compare like the masked region with some other random region in the field, to see if they sort of matched up in terms of the structure. But it doesn't seem like you do that at all. So I was just wondering, because that to me would be like how you would tell whether the LPI was working well or not.
Sorry, so you mean comparing the
like the filled-in region.
Yeah.
Whether the statistics of that are the same as some other sort of random place in the image.
Well, the thing that we want to like reconstruct is the actual filament itself. So here, like the WISE images serve as like the images of the ISM, so they're like point source removed and stuff. So we're looking to recreate structure that looks like the WISE image. So I think the right thing to do, like unless I'm understanding your question incorrectly, is like to compare to the initial image, because that's the truth for that region. Because we wouldn't want it to recreate some other random filament. We wanted to, yeah.
So this WISE actual data has not had anything removed from it?
So it's had like point sources removed and then some other corrections. So it's just it's like the dust map. Yeah.
Right. So I mean, okay.
Sorry, go ahead.
Okay, do we have any other questions? All right. If not, let's thank Devisree for a great talk. thank all of today's speakers for what a great job they did all this summer. And thank you, everyone, for coming and joining us today.
And I'd like to see the REU students for just 5 minutes to talk about computer accounts.
All right, thank you, everyone.
Before we leave, we have one brief note to make from the students ourselves. So we'd like to thank all of you who came today to support us. It really means a lot for you guys to spend your time listening to us and what we spent so much of our time working on and learning from. Thank you to all of our advisors, the other program directors who have supported us all summer. Thank you, of course, to Asase, who's been a huge support this entire summer in our writing process, and generally just making us feel at home. We, of course, want to give a particular thank you to Matt and Jonathan. For those of you who don't know, Matt is becoming OIR chair and is leaving the program, unfortunately, but has done a fantastic job in the past few years and is really near and dear to all of us as a personal and professional mentor. So for him, we have a book of letters from each of us, along with lots of photos throughout the summer, demonstrating our thanks. And of course, Jonathan has been doing this longer than any of us have been around. And his commitment, to education in this space and to helping us learn is, unmatched. So huge thanks to Jonathan. One of my personal projects this summer, as I got into photography, was cataloging the one other unmatched thing about him, which is his astronomy shirts. Every single day he comes in with either a new star field or an astronomy pun on. And yeah, the last page there will be lots of his shirts cataloged.
Not nearly all of them.
But yeah, so please.
I think that's an actual supplement paper.
Yeah, there's a slideshow with lots of them in it as well. Maybe we can play as we leave. But yeah, thank you to you all.
Appreciate that. Thank you. Thank you so much. I look forward to reading that.
You can't read it.
Yeah, that's Triani. You can just skip some of ours.
Read it in private when we're all gone.
I need cluster access. And if I go link to my Gmail, I prefer that. Damn it, because I backed everything up to the